So much. And also, I'd like to thank the CRM for the invitation, and Guillermo and Tim for putting it together. And it's always fun to be in Montreal as well, to be visiting here. So this model-based optimization, especially with convex composite functions, has been a theme for a long time in my research, going on 40 years now at different points. So I've had many collaborators on this over many years, and it's a topic which, well, we'll get to the sort of a little bit more of the history in a couple minutes. So see if I can reestablish this. Oh, there it went. Okay, so what is a convex composite functions, convex composite optimization, and model-based optimization? So the idea here is that you have an objective function that's taking this form with three ingredients, essentially, a function h, function g, and a function c that is in the composition with the function h. So h and g are both convex functions. We say a convex function is closed if it is lower semi-continuous. And we say if it's proper, if it never takes the value minus infinity, and at least at one point, it is finite valued. So it's not identically plus infinity. So proper means you're just getting rid of the trivial cases. Okay. And convex function, a convex function is a function such that this is the definition that you will learn mostly is if you take any 2 points on the graph and you take the secant line connecting them, and then that secant line lies entirely above the graph. Okay? But if you think about it, what this means is that if I look at the graph and fill it in, so that I take everything on or above the graph, that property of secant lines translates to any 2 points above the graph, and I can take the line segment connecting them, and that must lie in the set. Well, that is the definition of a convex set. Convex set is any set such that the line segment connecting any 2 points in the set is entirely contained in the set. Okay? Now, this set here, if this is your function f, okay, then this set is called EPIF, set of all pairs x mu, such that f of x is less than or equal to mu. Okay, so for a finite valued convex function, to say that it's proper simply means this is a non-empty set. Okay, so, and closed means that this set is closed. The epigraph is closed. Okay, so lower semi-continuity is the same in this case as to the closure of the epigraph. Okay, so note that I'm allowing these functions to take infinite values, but only plus infinity, because if a convex function is ever taking the value minus infinity, then essentially it's minus infinity and then plus infinity outside of it. It only takes on 2 values potentially. Okay, so those are not proper. And each of these pieces play a different role. So, oh, no. Yeah, here we go. I was afraid red wouldn't show. There it is, red. I think it's one hit. Oh, it's running through. So I'm going to have to go here. Oh, let me see. Oh, but I can't see things here either.
So it's actually because of the transition. So what I can do is actually get out of the full view. Okay, so you want the red and the next pages?
Well, the reds come in one at a time. So what's happening whenever I click it, it brings up 3 or 4 clicks simultaneously. So the clicks aren't coming in one at a time.
Okay. So what we're going to do? So basically the problem is this.
Yeah, this device.
Okay, I see. I'm going to change it. If you want, you can continue by clicking.
By clicking here.
Yeah,
that's what
I'm just going to change it. So
Okay, so what are the individual pieces? So the function h is what I'm going to call the model. Okay, so that's the model of the optimization problem. So as we'll see, there's many possible models in optimization. These can be nonlinear programming, minimax optimization, goal programming, least squares problems, or more generally, maximum likelihood problems and so forth. That's generally the model of the problem that you're looking at. And then the model, of course, you apply it to a particular function C. You apply it to the data. So I'm calling C the data that you're inputting into the model. But then there's other things that you might like the solution to satisfy, or there may be underlying prior information that you already know about the solution, okay, that you would like to include in the optimization problem, and that is the function G. So this is the regularizer, okay? So sparsity of a solution, or smoothness of the solution, or many other properties that one might wish to include. Now, although H and G are convex, this composition means this is no longer a convex problem. And it's because H may not be smooth and can be infinite valued. It's no longer a smooth optimization problem. Okay. And since H can be infinite valued, it can include constraints. So it turns out that most optimization problems, at least that are Lipschitzian, they behave stably with respect to changes in X, are of this form. So I'm going to go through a list of them, but let's first point out, for the simplicity of the formulas on the slide that we're presenting, note that I can subsume G into H. Okay, so if I define a function H tilde of two variables X and Y, then this is H of Y, this is G of X. If H and G are convex, the sum of two convex functions is convex, and I define C tilde to be C of X and X, then this composition is precisely this function. So what I'll be doing a lot here, well, for the most of the talk, I'll be hiding G. I'll be hiding the function G, okay? However, one must always be aware that, that again, oops. Oh, no, it doesn't work at all. Oh, there we go. That when we start talking about algorithms, it's absolutely essential to treat G explicitly, to include it in everything, because G is a fundamental function in how the solution behaves. And there's a lot of results that apply when H is finite valued, but G is infinite valued, and so forth. So there's a lot of key pieces there, but for the general presentation, it's fine to do this. Now, this is a very old problem. Perhaps an optimization. The first instance of this is the Gauss-Newton problem, okay, or the nonlinear least squares problem. And Gauss studied this problem in 1809 when he was attempting to determine the trajectory of the asteroid Ceres. And he claimed to have been working on it since the age of, using the technique since the age of 18. And also, Gauss was the person who made the connection to probability theory and Gaussian distributions, as one might guess. Okay, so, but there was a lot of buildup and work on problems of this class in the 1970s. And then in its full glory, in a certain sense, most of the fundamental theory was developed in the 80s and 90s. And then the whole area quieted down for a long time until about 2015, when all of a sudden it exploded and people were using it for all sorts of things. And so there's a few of the references are given here, but there's so many now, it's hard to. So the nonlinear least squares problem, here's a few examples. feasibility problems. So if I have a convex set C, then the distance to the convex set C, where this is the distance function, is a convex function. And so I can compose the C of x with the convex set C, and I get a convex composite function. This is related to trying to locate points x that are in C. If C is just 0, and the distance is given by the 2 norm, then this is again the linear least squares problem. Then there's nonlinear programming. Here, I'm going to be using the convex composite, the convex indicator function. This is a function indicator of the set C when C is convex. It's 0 when you're in the set, and it's plus infinity otherwise. So if I have the indicator of C hat of x here, that means I want to be in the set C. So it's a constrained optimization problem, a general nonlinear programming problem. That's the convex indicator. Exact penalization, so I can replace the indicator with the distance function. And then I can do smooth plus convex, which is a big class of problems now, championed by Nesterov, where you have a smooth function, not necessarily convex in this case, and you're adding to it your g of x for regularization. Okay, so robust phase retrieval problem is another instance.
This one should work.
Okay, is another instance. Sparse dictionary learning. Here are the arguments of the optimization problem are the dictionary matrix D and the vector R. And what you'd like to know is what you'd like to have is a sparse D and a sparse dictionary to represent the output data X, and you have to normalize, and typically there's other constraints on D that you can add. Then there's robust PCA, where you have a mask, you have certain information about a matrix. You don't necessarily have to know the full matrix, and you want to get a low rank estimator for that matrix. And again, you could have constraints here because you can see that if I multiply U by alpha and V by alpha inverse, then you get a multiplicity of solutions. And then this is a problem, hopefully I'll get some time to talk about this, sparse robust estimation, Kalman smoothing. And these functions here you can think of Z as data, you're optimizing over X, and V and W come from what's called the piecewise linear quadratic penalties. So in that case, we can think of partitioning the space into convex polyhedra, okay, and defining a quadratic function over each piece such that the whole function is then a convex function. Okay, so this gives us L1, least squares, elastic net, Vapnik, Huber, if you've heard of these kinds of functions. Okay, so one of the things in the model overall that we're looking at, h of c plus g of x, is that once you have the model and a method to solve a particular instance of h and g, then you can cycle through different datas. In other words, c of x's. Okay, but alternatively, you can switch out the regularizers and you can play there, or you can switch out h, the function itself, and play there. So h and g can be parameterized, and then you want to do some learning based upon which is the best choice within this model class. Okay, and that occurs in this application pretty frequently. So it's a modeling framework that allows you the freedom to have one engine or one interface, and you can play with the model in a number of ways. Okay, so outline, if I haven't get halfway through here, what I want to do is start from some simple ideas and then move on to algorithms, and then I'm going to spend time with the application at the end to illustrate the ideas. So the first thing when you have, and I'm subsuming G into H now, the first thing that you'd like to know is what is a first order necessary condition for optimality? In other words, a test. What are the critical points? And so forth. So a standard idea that one could apply here is that a first order condition, since I'm not necessarily smooth, I'm not going to use a derivative here directly, but a directional derivative, that sitting at a point X, if you're always looking up, then you're at a critical point. Okay, according to this first order information. And I'm going to take this very simple notion of directional derivative. Okay, so in certain cases, this is fine, but as we'll see in general, it's not quite sufficient to just look at this directional derivative. But let's now ask the question, for this class of functions, does this object even exist? Okay, so for that, I'm going to go back to convex functions. And notice that I have the secant line. Okay, and when I bring this point down, okay, the slope increases. Okay, or sorry, decreases. So because the slope is here and it's decreasing. Okay, so these slopes of those lines are non-decreasing in my distance from the base point. Okay, so when now I look at the directional derivative, I get that this is a non-decreasing function of t. So that means the limit actually equals the infimum. And the infimum will always exist. But it could be minus infinity. But it will always exist. Okay, so for convex functions, the directional derivative always exists at every point in all directions, at every point in the domain in all directions. And it could be plus or minus infinity. Okay, one extra piece, which the proof is similar, a little bit more complicated and detailed, is that convex functions, if I assume this convex function is finite dimensional, okay, finite everywhere, finite valued everywhere, not just finite dimensional, okay, then it is always locally Lipschitz. That means every point has a neighborhood about it, and a value L such the difference in the function values are bounded by L times the difference in the base points. So I'm going to use those two facts to study the directional differentiability of a finite valued convex composite function. So H is convex. So I can look at the difference between H at C of X and H at the linearization of C of X is Lipschitz. So I have this, and now I have the difference between a function and its linearization, and that's just little o. Okay, so what I get is that H of C of X, or f of X, at any point is H of the linearization plus little o. This is a convex function of X. Okay, so this non-convex function is up to little o, approximatable by a convex function. So, but I know the derivative, the directional derivative of convex functions. So the directional derivative of this function is this limit. And I know the difference is little o, so I can take this and replace the linearization. And now I have the directional derivative of a convex function. And here is the directional derivative. So I have, to get the directional derivative, I just apply a chain rule. So a chain rule holds for the directional derivative. So to go further for non-finite valued convex functions, I'm going to need a little bit of background, convexity. And I'm going to do that using these functions, where you give me a set, and then I take the supremum, I evaluate this function at z by taking the supremum over the entire set of zx. Okay? So what I'm saying is I'm picking a direction z, and I want to go as far as I can, and yet still stay in the set. Okay? So for those familiar with linear programming, that's just a linear program when S is a polyhedral convex set, and you can generalize it to basically any set. But notice that when I take the supremum, I might as well take the supremum over the closed convex hull of that set. So the support function of any set is the same as the support function of its closed convex hull. So there's this relationship that I showed you before between a convex function and its epigraph. So we can look at the support function to the epigraph of a convex function. Okay, so I'll pick a, but notice that this goes up to infinity. So when I take the support function, if I ever have a positive term here, I'm guaranteed that the value of support function is plus infinity. So I want this second term to be negative, and I'll just normalize it to be -1. Okay, so now I'm going to look down. There's my z -1, and I'm going to evaluate the support function. And what I'm going to get is going as far as I can, okay, and I'll get something that looks like this. And notice that looks like a tangent to the epigraph in some sense. This looks like some kind of tangent to the set. So there's a language associated with that, and that is at this point where you achieve the supremum, we say that the closed convex hull is supported by that hyperplane determined by z. Okay, so those are supporting hyperplanes to a convex set. And here we have these supporting hyperplanes to the epigraph. And that gives us some variational information, just like a tangent line does, about the convex function. Now, if we multiply this out, what do we get? What is that function, which I'm defining to be the conjugate function of phi? Okay, notice if I just multiply it out, I get this expression. So it's the supremum over all x of this object. Now, for every z, this is just the collection of lines. So I'm taking this, and these linear functions they're all convex. So this is the supremum of a collection of convex functions. And the supremum of any collection of convex functions, pointwise supremum, is a convex function, because it's the intersection of the epigraphs of all those functions. Right? So this is a closed, because it's supremum, convex function. And it's proper as long as this is finite valued somewhere. Okay? And that's called the convex conjugate. And it's the fundamental object in the duality theory of convex optimization. So remember, when we talk about convex sets, every line segment determined by 2 points in the set is contained in the set. Okay? But dually, convex sets have another way of thinking about them. The dual way of thinking about a convex function, okay, is that it is the intersection of all closed half spaces that contain the set. That's an external understanding of a convex set from points outside the set. And that's the dual object. Okay? So what we have is that for every x, this is bigger than this. That means I can take this to the other side for every x, and I get this expression. And the only way you can get equality here, remember, because I can bring this over to the other side, is if phi of x is the second conjugate of x. That's the only way you can get equality. Okay? But that means the second conjugate equals phi of x. So I conjugate, and when do you get equality? Well, you get equality when we have the closed convex hull, so you get attainment. Okay, so you get equality when the epigraph is a closed convex set. And we call that a closed proper convex function. So for every closed proper convex function, phi is the second dual. second conjugate. So that's the biconjugacy theorem. So the epigraph of the second conjugate is the closed convex hull of the epigraph of the function. So we always have this is true. And if in addition, this is already a closed convex set, then we get equality. Okay. But we get more because we know there's this relationship to supporting hyperplanes at the points where the supremum is achieved. So let's look at that. So here we have the convex conjugate again. And suppose we look at one of these points where the supremum is achieved. That says at that point, this is always bigger than or equal to this for all other x's. Well, let's just move things around. That's the same as saying that this affine function lies entirely below the graph of the function and touches the graph of the function at x bar. Okay, well, that's what that picture's saying. So it's giving you automatically this variational information associated with the epigraph at every given point, the set of points where that's attained. So the set of all such, given an x bar, the set of all z's that do that, there may be more than one, we call the subdifferential. Okay? Because you get these things touch the graph and lie entirely below the graph. And there may be many of them. So for example, in this picture here, I have one here, here. It's all those slopes. So there's many possible z's at points of non-differentiability. And there's a nice relationship between the subdifferential, because now we have another convex, and we can again look at its support function. Let me step back for a minute. So notice we're in the subdifferential, if and only if we get equality here, okay? But that's symmetric in phi and phi star. So the only way this can be true is if this is true. Z is in the subdifferential of phi of x, if and only if x is in the subdifferential of the conjugate at z. That's an amazing thing that allows us to switch that relationship back and forth at will. Okay? One more thing, the next slide. The support function of the subdifferential is the directional derivative. You have to prove that. It's not, but this, so this, I'm going to sweep this under the rug a little bit. A few things will get swept under the rug. Okay, so now what do we have? We have the directional derivative of the convex composite function is given by this chain rule, but this is a support function. So it's the support function of that set. So the convex we get that's the directional, so we can define that object to be the subdifferential. Now, we normally don't define it that way. We usually go out and use generalized subdifferential theory to get it, but this is the same as the Clark, the generalized, the proximal, limiting, Mordovich subdifferential, they all reduce to the same thing in this case. So what happens, so that was all for finite valued H. When it's not finite valued, things can go wrong, okay? So we have to be careful. They can go wrong for a multiplicity of reasons, okay? So if it's not finite valued, then the domain, we define this to be the central domain of H, wherever it's finite valued, when it's not the whole space, okay? Then it's plus infinity outside of this set. So to fix this, what I have to do is work with this domain set. Notice that if I look at if I take the affine hull of a convex set, that is the smallest affine set that contains it. So an affine set is just a translative of subspace. That's what an affine set is. Okay, it's translative of subspace. So I look at that translative of subspace. Okay, the smallest one that contains the set C. So the intersection of all affine sets that contain C, that's the affine hull. Okay? And then I can look at the topology relative to the affine set for a set C. So we say the relative interior is the interior relative to the affine hull, and the relative boundary is the boundary relative to the affine hull. So notice, if I know properties of a convex function on the whole space, I can apply that to the affine hull, because I can take the affine hull and shift it to the parallel subspace by simply subtracting a translation. And then basically I'm just working in a subspace, and so I can just work in the relative topology of the subspace and apply all those facts I know about convex functions that are finite valued to get it for infinite valued ones. So, but still, the directional derivative does not adequately describe the behavior on the boundary, because I can take a very simple convex function, a convex indicator function of the unit ball, and the directional derivative in any one of these directions is going to be plus infinity, because you're just looking at a line, along a line emanating from that point. Okay? But I want a more robust concept of directional derivative. So what I want to do is I want to take limits of things that converge. And I need to take the infimum of those limits, and that's called the subderivative. So the subderivative is like it's kind of a directional derivative, but now I let the d's converge, t's go to 0, and I take the limit infimum of this object. In that case, these directional derivatives are going to be 0 in those directions rather than plus infinity. Okay, so there's another problem, not just the existence of these directional derivatives, but also the relationship between H and C may be bad, in the sense that if I look at the linearization of C and I want to compose that with H, there may not exist an X tilde that puts me into the relative interior of the domain. In other words, in a sense, the linearization of C is not transversal to the relative boundary of the domain of H. And when that happens, you're singular in a sense. Okay? So what we need to do is come up with something that avoids this fundamental problem. Okay? And that is typically called a constraint qualification. Okay? So constraint qualifications are employed to correct this problem and other problems. Okay, so the basic constraint qualification in this context is that the kernel of the adjoint of the Jacobian of C intersect this thing called a normal cone to the domain has got to be 0. And the normal cone is simply the subdifferential of the indicator, and it's the set of all angles that form an angle greater than or equal to 90 degrees of vectors that point into the set. Okay? So for all z's that form an angle of greater than or equal to 90 degrees of things that point into the set is called a normal direction. So if we look at this thing, we look at these tangent lines here, I got to form an angle of greater than or 90 degrees with all those lines. So those angles form the normal cone. Okay. So, so this is related to, because of this tangential condition, a transversality condition. Okay. So notice that if the domain is the whole space, okay, then the normal cone just reduces to 0. Okay, so there's no condition required. Okay, and if it's, well, then there's other cases, but let's move on. So turns out that when the constraint qualification is satisfied, then we get a chain rule for the subdifferential, and we get that the subderivative is now the support function of the subdifferential. Okay, so we have a calculus going on. We have a chain rule. So we have a rich calculus. The basic constraint qualification also says, remember the subdifferential is the adjoint applied to things in the subdifferential. So we're going to be concerned with those things in the subdifferential for which the subgradient elements are attached. And it turns out that the basic constraint qualification is satisfied if and only if this is a compact set for every V in the subdifferential. Okay, and that's another important thing. Constraint qualifications are always very technical, so understanding it can take a very long time. But this is how we get away from singularities. One way to think of it, if you know about nonlinear programming, remember not standard constrained optimization, the basic constraint qualification is what's called the Mangasarian-Fromworth constraint qualification. That's the standard constraint qualification that's used in nonlinear programming. Okay, so now we're going to move on to Lagrangian theory. So for this problem, I'm going to define the Lagrangian, and Y will be the Lagrange multipliers of Y C of X minus the conjugate applied to Y. And why is this a natural thing to call the Lagrangian? Well, because these are the things that you take the supremum of in Y to get H. Now, if you have a regularizer, there's a couple of ways you can fix up the Lagrangian. You can either do the same thing to G, or you can leave G alone. I'm not going to go into these, but in applications, this becomes very important, which Lagrangian you choose to get the right dual problems. But, so what I have again is that H composed with C of X. Remember, H is closed proper convex, so it equals its second conjugate. Okay, so now I have min sup of the Lagrangian. And this is how you get the duality theory and how you get the dual problem. And what is the dual problem? Well, you just switch sup and min. And that's the dual problem. Okay, so first order optimality conditions. The subderivative is bigger than or equal to 0 is the same as same because that's the support function of this set. 0 is in there. It's the same as saying 0 is an element of this. And then we can twist this. If I take the derivative in X, this is C transpose XY. It's got to be 0, but where's Y? Take the derivative in Y. C of X is in the subdifferential of the conjugate at Y. But to be in the subdifferential of the conjugate of Y says that Y is in the subdifferential of the function itself at C of X. Okay, so this is Lagrangian optimality conditions for problems of this type by using this twist. And again, you recover Lagrangian optimality conditions in terms of the Karush-Tucker conditions or KKT conditions for the general nonlinear programming problem, as well as all these other minimax problems and goal programming problems and so forth. Okay, so now let's look at the smooth case. So F is here, gradient of F is given that way. Here's Lagrangian. There are the optimality conditions. If I unravel these optimality conditions, using again this property, then I can write it this way, but it's differentiable, so I write this, but that's precisely the gradient. So the gradient is 0. It's the same as the first order optimality conditions. Okay. So the elements of the subdifferential of H turn out to be the Lagrange multipliers. Okay. Now we move on to a second order theory. I look at usually associated with the Hessian of the Lagrangian. Right? So I have Lagrangian, take the second derivative in X, simply Y times the Hessians of the individual function Ci. But now if I take the second derivative of F, I actually get two pieces. Okay, and remember, these are the objects associated with y. So this is only including the curvature of the data functions, the CI. It is not including the curvature of H. Okay, so in a second order condition, somehow I got to get this curvature of H in there. So H is not necessarily differentiable. So how am I going to get second derivative? So I define this object, and these are the multipliers. So it turns out that if you're at a local solution, that means you're first order optimal, and you have a second order necessary condition. So the question is, when I replace that with a strict inequality, do I get a second order sufficiency condition? And that's so far only known for piecewise linear quadratic functions, and sufficiency is satisfied. Okay. So algorithms. So what do? We do what Gauss did. We linearize inside of H, and then we add something here as a curvature term associated typically with the Lagrangian. So Newton-like method would do this. We know it's kind of missing this second order term for H, but if H is piecewise linear, that H double prime is identically zero. The Prox linear algorithms, you just take a multiple of the identity. And this problem is convex depending upon whether H is positive semi-definite or not. So you have to be careful there. In the piecewise linear quadratic case, we get local quadratic convergence of an algorithm that does this when you put in the Hessian and Lagrangian. And when you just have BFGS, a matrix secant object in there, you can get superlinear convergence. So if we apply it to general, this is the nonlinear programming problem again. This is the convex-composite framework. Then we put a linearization of C inside the indicator. So that means we have linearized constraints, and we put it in here for phi, we linearize phi, and we add on second order term. Okay. And that is called sequential quadratic programming. So those results on the previous page establish the convergence properties of these algorithms. In the sharp case, what time is it? How many more minutes?
13.
13 minutes? Okay, so I'll move away from the sharp case, but sharp means that you move at a linear rate away from the minimum value. In that case, you can subsume the curvature condition in H, and you get an algorithm that's under this condition. You get both existence of solutions and quadratic convergence. Okay. So the next thing is, so this is how you update, and we know this is kind of like a Newton method, but you need a way to globalize because it may not give you, the update may not give you descent in the function. So when we look at an object here, this is the inner linearization minus the function value, okay? We know that this object gives us the directional derivative, especially if you take the infimum over t, it is the directional derivative. But it has the advantage of being continuous. Well, this is finite valued, say. It's continuous in both x and d, and it's continuous on the relative interior of the domain of G. So we get a continuity property of this, which we do not get for the directional derivative. But we can use it as a substitute for the directional derivative. Okay, so we know this is true. Okay, and now I'm going to choose a d associated with minimizing this object to d by restraining its magnitude. It's like a steepest descent direction, but using delta instead of the directional derivative. And then this is, I don't know if you know what backtracking algorithm is. So instead of the directional derivative, for example, if I bring this over to the other side, I divide by t, sigmas between 0 and 1, then this is the infimum of these guys, so that you know after a finite number of tests of t, this inequality will be satisfied, and I will reduce the function value. So I put in the, I guess this is supposed to be, so I put in this inequality. This is the same as the Armijo-Goldstein inequality, but then I require an extra curvature condition is satisfied, and I can do this entirely in terms of this continuous function. And then trust region algorithm. So probably everybody doesn't know all of these classes of algorithms, but in each class, you can use the delta instead of the directional derivative because you have non-differentiability. And then you can establish convergence properties for each. Basically, in the limit, you get a stationarity condition is satisfied. That is, this is driven to 0, essentially. And if you have a cluster point, that means first order optimality. Okay, so I'm going through this part really quickly because I want to move on. Okay, so this is a result of Dima Drusiewski and Courtney Paquette. You may know Courtney, and this was part of her thesis. And I think I should probably let Courtney describe this to you. There's not a lot of time left, but basically they get an iteration complexity on an optimality object for these iterates in the Prox-linear algorithm, where H is a multiple of the identity. Okay, and you only need approximate solutions. That's a recent result. Okay, and then there's a Davis-Drusiewski, Adducci-Ron result where they do this for stochastic convex composite, where they just take a single sample, form this subproblem, just one sample C, stochastic gradient descent, okay, in this case, but it's stochastic Prox-linear, and they're able to get an iteration complexity result. And that's a pretty astonishing, very recent result with recent modifications. Okay, so I want to get to this example. And it's the common, because I want to show how you can play with the model to get other aspects of the problem. So Kalman smoothing. So what you have is a state of a system, airplane, boat, a drug in the body, whatever. And those are the states that evolve over time, states that evolve over time. And you go from one state to the next using a transition function. Okay, but you never get to see the state. All you get to do is apply some function to the state, or you get the result of an application of a function to the state, and you get an observation. So the Z's are the observations. Knowing the observations, the functions H and the functions G, can you recover the state? Okay, but you don't really know the relationships. They're not really tight. There's endless applications. They're not really tight. You only know them up to error. And you quantify these errors, okay, typically as Gaussian. So these errors come from a stochastic model of state transition, which is typically related to a stochastic differential equation. And the V's are observation error because the H is some machine that you're applying. Like you're flying an airplane and you're looking at wind speed, you're looking at altitude and so forth. Those are the things you kind of know about the state, but there's always some error there, okay? And then you make these Gaussian assumptions in the classical framework, and you want to recover the unknown states. So what you can do is a maximum a posteriori estimate using maximum likelihood, okay? So in the original classical approach, these transitions were all linear functions of the states, and the observations are all linear functions of the states. Okay, so, and then you recover using each time you get to the next step by using the previous steps as a prior, and you recover. And when you do that, the linear algebra associated is given by this. This is called the Kalman gain matrix. I don't know if you've heard of any of this. But there's a completely different way of thinking about this. And that is an optimization perspective where you just write down the joint. So this is a joint probability. You're trying to estimate these given these. And that's proportional to the observations given the x's times the probability of the x's, which you can simply write out because you've specified the underlying normality of the errors. Okay. And you get this problem. When I take the negative log likelihood. So you're maximizing the probability of observing this data. What are the x's that maximize the probability of observing that data? Okay. So you can clean it up a lot by defining a g and an h, putting these component-wise, defining these objects. And then it's just a nonlinear least squares problem, where I've changed the inner product a little bit in terms of the covariance matrices. Okay. So it's just a big nonlinear, well, it's a linear because if I assume the classical setting. So if I assume the classical setting, then these are linear mappings. Okay, so I just differentiate and set the derivative equal to 0, and I get this object. Okay, where the g's and h's, these are the diagonal, this is a big G, lower bidiagonal. And that structure implies something very important about that matrix. It turns out that that matrix, the matrix you have to invert to get the state, is block tridiagonal. Okay? So there's special solvers for block tridiagonal systems. Okay? So if you just want to get the final state, the last state estimate, that's called the Kalman filter, because you're moving along and you want to know what's going to happen next, and that's all you need to know to make your decision. Okay? And but the smoother is you actually recover all the states. So one way is to do a forward solve, and you can get this, and then you do a backward solve, and you get the full state. And doing a backward solve is exactly the Kalman filter update. It's numerically the same, but there's many other ways to do it for block tridiagonal systems. Some are more numerically stable than others, depending upon the input data. Okay, so this is why it's called a smoother, because I'm going to assume I have a smooth transition with this is Brownian motion. Okay, so that's white noise. And I want to estimate the state and the derivative. So I'm assuming there's an underlying smooth function that's giving me the state, and I want to find that function. Okay, so since it's coming from Brownian motion, I know what the variance Q is. H is the observations, but that's some machine that's giving me the observations. In this case, it's the actual state itself that I can see, but I don't know the derivative. Okay, and I can throw in this variance, and so what we get is the circles, which is the data. The red line is the smooth action, and I need to recover the red lines. So I assume everything here is Gaussian, and the recover gives the blue dotted line. That's the solution given by the Kalman Busey filter. Okay. However, that assumes Gaussian, and it assumes a bunch of other things. There's no state constraints, but in practice, there's often state. You're tracking an airplane, and you know it's not going below the surface of the Earth, okay? Or a boat, it stays in the ocean. Well, sometimes. And so forth. So there's typically state constraints, and also densities are not, it's not always Gaussian. So what happens when you're non-Gaussian? Okay, there can be trend shifts, there could be outliers, there could be all sorts of stuff. The covariance may be state dependent. So an aircraft changes its angle, and your ability to identify it varies depending upon its angle of attack. Okay, and then there's hyperpriors and so forth that one might be interested in incorporating. So that's the nice thing about the model. Okay, so here we have, again, it's the same sign. Okay, there's outlier data. These are the circles. They're actually off the chart sometimes, but this is where they are. That's all the circle is telling you. The pluses are the true data. Okay, And notice in this case that there's some outliers heavy at the end with none down here. So if you do a Kalman filter, assuming Gaussian information, that's this dashed line. Okay. If you do outlier trimming, three deviations or more from this curve, then you throw it out and then you resolve, outlier trimming, then you get this dotted line. It is totally pulled by the outliers. So this is a problem in the Kalman filtering setting with any trimming of outliers at all. Okay. So, but if you use a non-Gaussian distribution, in this case, the Laplace distribution, which I'll show you what that means, you get this thin line and you can track pretty well. Okay, so it's a robust density is now being used, non-Gaussian. And so this is the Gaussian. What I'm going to do is use the L1 norm. That's Laplace, underlying density is Laplace density. And that's how I got that black line. Okay. The problem is, how do you solve this problem? Okay. So in general, we can put different functions in here. And I'm going to put in the piecewise linear quadratic class. Okay. And there's a question of when they define a log concave function. So such things in the class are Huber, Vapnik. There's a whole bunch of stuff you can throw into this class. And this is what a piecewise linear quadratic function looks like. It looks like the conjugate of a quadratic function evaluated on an affine image. And it's this condition which guarantees when this actually produces a log concave density. It's a technical condition that okay. It turns out when you go to solve these problems, you get a system, you get a KKT conditions that look like this. And this is called the complementarity condition. This is highly non-smooth. But I can perturb this by adding something here. And that gives me the interior point algorithm. So if I do the interior point algorithm to this system, okay, how hard is that to solve? That's a problem with interior point. Well, it turns out you recover the exact same tridiagonal, block tridiagonal system. And you can use the exact same algorithms to solve it, but you have to solve it iteratively. Okay. And fortunately, the interior point's fast, and that's how this was obtained. Quickly go through other ones. You can have a trend shift. Okay. And you can track it well using a piecewise linear density. You can, let's see, where am I going with this? When the nonlinear, you can also do nonlinear by doing the Gauss-Newton method. And so this is, I've done, here's a nonlinear. This is a van der Pol oscillator. And again, we can solve, we can have outliers and still solve fairly accurately. And you can have constraints. You can throw them in. You still get a tridiagonal system to solve, block tridiagonal system to solve. And they can be nonlinear constraints, in this case, linear constraints. And that's it. I think I went over time, but I don't know how much by. Thank you. The last part went really, half of it probably went really fast, but anyway. Any questions? Yeah.
Thank you for the great talk. So the initial, probably the first slide or something, you have this general problem, right? H of C
Yes.
with GX. And the assumption of C is that it's C2 smooth, right?
Well, you don't always have to assume C2 smooth. So a lot of this is just C1. It's only when you want to get to second order information that you assume C2. And that's only for getting higher rates of convergence, except if you can prove the problem is sharp. The problem is sharp, you can get high rate. That was just that you grow linearly away from the optimal set of solutions for the function H.
Okay, so that can actually be relaxed, like C1 smooth.
Yes, and you can even relax it further, but I didn't want to go out into the full realm of variational analysis where you use generalized Jacobians.
Yeah, because that, okay, my follow-up question is, okay, everyone talks about deep learning these days, right? So does that fit into that framework if we remove some smoothness from C? I think so. Right?
Yes. So you can do, yes. So there's some deep learning, yes, deep learning applications are fall under this because the inside function is, you know, depends on what class of functions you're using, but yes. And they can be non-smooth.
Yeah.
However, they behave nicely. They're non-smooth, they're nice and quantifiable. And so you can compute generalized Jacobians. In fact, they're semi-smooth.
Yes.
Yeah, so since they're semi-smooth, I showed you you linearize inside, but with a semi-smooth, there's a kind of linearization you can apply, and you just put that in there. And then, you know, Newton works. So if you have semi-smoothness plus sharpness, you get superlinear convergence. So, yeah. Any other questions? Thank you.
Excellent. Thanks again for delivering this talk. So mine actually took my first question, but my other question is kind of silly. How do you get, so you said that it is correct for the characteristic function of the ball, and you verify things first the limits as to the direction.
Yes, so if you only take the directional derivative, you're only moving in the direction d, and you immediately go up to plus infinity. Okay, so but instead, okay, so now that allows me to wiggle this thing, right? And you're going to take lim inf over these, lim inf. So you're looking at the smallest values of these limits. And you can show, I don't know if you know, that this is a sublinear function. So once you know, when you take this lim inf and you know it's sublinear, then you know it's the support function. Hormander's theorem says it's a support function of some convex set. And it turns out that that convex set that it's a support function of is the subdifference. In this case, when you have the basic constraint qualification holding. And the basic constraint, the constraint qualification is general because H is not finite valued. So it has, its domain is imposing a constraint. And so somehow the linearization has to be able to hit that thing transversely. It has to be able to hit the boundary transversely. It's because if it's tangential, you can't move and stay in the set. So that's the reason for a basic constraint qualification. Okay, so, and it also immediately gives you that you can attain points in the set from outside the set. So, yeah, because it's a local, basic constraint qualification is a local property. Is that it?
I mean, I think it's very interesting in sensitivity, all kinds of problems. But so what we, Simone and I have been working on the structure is the additive composite one, where one part is smooth and the parameters are always the smooth part.
Yes.
Now, if let's take the easy model like phi of f, okay.
Yeah.
F is the smooth part, phi is the. I can still say, okay, f is actually a function of x and p. Yeah. So yeah, you call it C. Oh, okay. Well, okay, so now the parameter is clearly not entering, like, I mean, inside it's entering smoothly, but
You don't have to have it smooth.
we still hit, you hit it with a nonsmooth function. Like any insight as to how to approach the perturbation analysis?
Yes, so under the constraint qualification, again, the multipliers act as derivative elements or subdifferential elements for the optimal value function, right? So you would then have to say, well, does a chain rule apply to this function theta? Okay, so if it's a linear perturbation, okay, then yes, okay. If it's nonlinear, then you're going to have to add something on top of to make sure that there's even more stability. There's even more stability. So that was the key. The basic constraint qualification is equivalent to saying that the multipliers are always from a compact set. And so you get the Lipschitz constant is the diameter of the convex set that it's contained into. Mm-hmm.
But of course, that's the optimal value function. We're all about optimal solution function.
The optimal solution function requires, unfortunately, higher order information on the stuff in the inside. And so that you can say a lot, as you well know, with second order information, but also weak convexity helps you if you can get some higher order information directly out of that, as well as sharpness. Sharpness will also give it to you. So there's a, yeah. That's why those two things keep on popping up.
Any question? Yeah.
Yeah.
First of all, thank you for the talk. I have a question about the algorithm.
Yes.
So basically, you have some guarantee of that the algorithm will converge to the first order stationary point.
Correct.
Is there a way to avoid the strict saddle point, for example, using the second order stationary point? The second order optimality condition.
Yes, you can avoid. So I would have to go back to the second order theory, but you can avoid. You can. Yeah. So the saddle point theory is going to come out of Lagrangian, but it's not. I have to go back to the. Oh no, it's up this way. Okay. So the easiest thing to look at. Where's the second order theory? Here it is. The easiest thing to look at is when H is piecewise affine, because then this piece disappears. Okay, but unfortunately, the second order term involves all the multipliers. With the basic constraint qualification, you know that's a compact set, but still you have this object. Nonetheless, you will know you can avoid points where this is not true. Okay, and you can avoid it by adding on. What is algorithms? Something that's related in the piecewise affine H case by having a good approximation of the Hessian Lagrangian, and then choosing from the subprop. So okay, so where do you get the YK? I never told you where you get the YK. So there's a number of ways to get it, but in general, you solve this problem. Okay, it will automatically give you a YK. Okay, because you'll have zeros in the subdifferential of this object, okay? If you have what's called LICQ, or the linear independence constraint qualification, which is stronger than the basic constraint qualification, then the multiplier is unique, and you'll be able to avoid points that don't satisfy second order necessary conditions for optimality. It's not all the way, I mean, you never know whether you're going to be sufficient or not, so that's about the best you can do. And,
because in the smooth case, we can guarantee, I think, that the high probability that would escape this thing.
yeah.
But they have a similar result here.
Yeah, so there is, I can't remember, I'd have to go back and dig that up. I should have brought that up. I think it was done by the group at Louvain in Belgium, right? Philippe Toin. I think they have a paper on how to avoid, on that result, on how to get rid of it, but I'm almost certain they require the uniqueness of the multiplier, because otherwise you get stuck with the property that you got to take the maximum over all multipliers. Of course, if you know it's true for one multiplier, then the maximum is positive, but you might not have picked the right one.
Are there any other questions? Any questions from the online audience? Okay, I think